Hi, in this video we're going to have a look at how we can work out the tension in a string when we've got vertical circular motion. So for example, in this situation I've got a particle that is travelling around in a vertical circle, and the particle is going to move from A to E. At A we know it's going at 8 meters per second, and what we want to know is what the tension in the string is when it gets to point E. Now in this video I'm going to take you back to a very basic problem, and we're going to have a look at all the skills that we need to be able to solve this problem. We need to be able to deal with the energy in the system, as well as using Newton's second law radially, and that means towards the center of the circle. Right, so let's go back to the beginning. Now we're going to simplify this problem. So we've got a particle of mass 0.1 kilogram that's initially hanging vertically from a string of length 50 centimeters, so 0.5 meters. It's given an initial speed of 8 meters per second, as we mentioned before, and we're going to first of all work out the speed of the particle at B, which is here, which is at 90 degrees, and then also at C, which is vertically above A. So our first job here is we want to work out how much energy is in the system. Now because this is a closed system, which means that there isn't any energy lost within this system, that means that any energy that we find is always going to remain the same throughout. So the amount of energy in the system won't change. So if I can work out what it is at A, and work out what the total energy is at A, it will be the same at B, it will be the same at C, and it will be the same at any point in between as well. So we're going to take our reference for potential energy is equal to 0 at the base at the bottom, which is sensible. So the only other energy that's going to be working here is going to be our kinetic energy, and we can work that out by working out half mv squared. So at A, my energy, or my total energy, I'll call it, total energy is going to be equal to, and it's just going to be the kinetic energy, which is half mv squared. So that's going to be a half of the mass, which is 0.1 times v squared, which is 8 squared. Okay, so if I work that out, that's going to be half of 64, which is 32 times 0.1, which is 3.2 joules. I can use my calculator for that if I wanted to, but I'll write down 3.2 joules. Okay, so that's the total energy in the system, and that's going to stay the same throughout. So it doesn't matter where I am now, where my particle is, that's going to be its total energy. So we can use that information now to work out what the speed is going to be at particle B, because at particle B, well, the total energy is still going to be 3.2 joules, and there will be kinetic energy, but there'll also be gravitational potential energy as well. So I could say my total energy, which is 3.2, is going to be equal to, and it's going to be mgh, write it down, mgh plus a half of m and the velocity at b squared. So I can substitute the values that I know, which is going to be, well, mgh is going to be the mass, which is 0.1, times gravity, which is 9.8, times the height, which is 0.5, plus a half of the mass, which is 0.1, and then the velocity of b squared. So if I work this out, I've got my calculator this time. So we've got 0.1 times 9.8 times 0.5 that's going to be 0.49 plus 0.05 v squared. Okay, so if I now do 3.2 take away 0.49 and then divide by 0.05, and that gives me 54.2. so v squared is equal to 54.2, and then I can work out that v is going to be equal to the square root of that, which is 7.36 meters per second. Okay, now I've deliberately written down what v squared is at b, because that's something that we will need later on. So that's going to be at b, and also at c we're going to do a similar thing. I'll use a different colour. So at c we've got our total energy, which is 3.2, is going to be equal to mgh plus a half of and the velocity of c squared. Okay, so this time our height's going to be different. This time we have a height of 1, so we're going to have 3.2 is equal to mg, which is going to be 0.1 times 9.8 times h, which is 1, plus a half of 0.1, and that's going to be vc squared. So tidying that up, we've got 3.2 is equal to, and that's going to be 0.98 plus 0.05 velocity of c squared. So to work out the velocity of c squared, that's going to be equal to, and we've got 3.2 take away 0.98 and divide that by 0.05, and that gives us 44.4, which means that the velocity at c is going to be equal to the square root of that, and that gives us 6.66 meters per second. 6.66 meters per second. Okay, so we'll just check those. Got 7.36 meters per second there, and 6.66 meters per second there. Okay, so the key thing here is that the energy doesn't change. So even if we were over here, we know the total energy is 3.2 joules. So even if we were over here at this point D, well, we should still be able to work this out. So let's just have a quick go at this. I know my total energy is going to be 3.2 joules, so I'm just going to write that down to remind myself. Okay, and now at point D, I need to work out what this distance here is, because I need to know what the height is. So the height is going to be given by, well, this distance here is 0.5 meters because it's the radius. Yeah, so it's going to be the same as this, that distance. Okay, and I need to know what this distance here is. And I can work that out by doing 0.5 cos 35. That will tell me this distance here. And if I take that away from 0.5, that's going to tell me what this distance here is. So to work out the height here, I'm going to do 0.5 take away 0.5 cos 35. Okay, so that's going to tell me my height, and I'll work that out first. So that's going to be 0.5 take away 0.5 cos 35, and that gives us the distance of a height of 0.0904. Okay, so we now know what this height here is, and what we're now going to do is we're going to say that our total energy, so 3.2, is going to be equal to mgh plus a half mvd squared, and that's 3.2 is equal to the mass, which is 0.1 times 9.8 times the height, which we've just worked out to be 0.0904, plus a half m, so I'm just going to put that straight in, so the mass is 0.1, so that's going to be 0.05 vd squared. Okay, so again, now I'm just going to put this straight into my calculator this time. I'll use this number that I've had stored into my calculator, so I'm now going to times this number by 0.199.8, which gives me that there, so that's the value of this here. I'm now going to do 3.2 take away that, and that's going to tell me what this bit here is equal to. So I divide that by 0.0, and that gives me a value of v squared of 62.2. I'm just going to write that down. So vd is going to be equal to 62.2. Sorry, vd squared is going to be equal to 62.2. So that tells me my velocity at d is going to be equal to the square root of this, which is 7.89. 7.89 meters per second. Okay, and I can just check that over here, and it is indeed 7.89 meters per second. Right, so, and we can use a similar method to work out the speed at any of these places. So what we're now able to do is, knowing what this initial speed is at the start, and using that to work out the total energy in the system, we're now able to work out the speed at any point around the circle. So we're now going to have a look at how we can use what we've done so far to help us work out what the tension in the string is at any given point. So first of all, we're going to have a look at point A over here. We're going to apply Newton's second law radially, so that means towards the centre of the circle, to work out the tension in the string at A. So it's important that we realise that we're always going towards the centre of the circle when we're using Newton's second law radially. So let's have a think about what's going on here. So if I mark a diagram here, I'm going to have my tension that's going towards the centre of the circle, and I'm also going to have my weight, we'll call that mg for the time being, that's going to be going vertically downwards as well. So to work out the tension in the string at A, I need to use Newton's second law, which is force is equal to mass times acceleration. Remember, acceleration is v squared over r, so I'm going to use this here, which is my force is equal to mv squared over r, and the F here stands for the net force. It's always about the net force. Okay, so let's move this back over here. Okay, so my net force here, taking our positive direction towards the centre of the circle, my net force is going to be my tension, which is the positive part of it, take away my weight, which is mg. Okay, so that's going to give me my net force. So I'll write that down. My tension take away mg is my net force, and that's going to be equal to mv squared over r. Okay, and that's my velocity at A, I should point out. Okay, right, so I know my mass and gravity, and I know the radius of my circle, and I also know the velocity of A, because that's my initial velocity, which is 8 meters per second. So I've got all the information that I need to work out the tension, so I can say that my tension take away 0.1 times 9.8, which is 0.98, is going to be equal to m times velocity of a squared. So the velocity of a squared is going to be 64, and I want to times that by the mass, so it's going to be 0.1 times 64, which is 6.4, divided by the radius, which is 0.5. So my tension is going to be equal to, and that's going to be 12.8, I'll put it down, so 6.4 divided by 0.5, which is 12.8, and I'm going to add on 0.98. And that gives me 13.78, so my tension is going to be equal to 13.78 newtons. And just check that that's what we've got over there, 13.78 newton. Okay, so we also want to know what the tension in the string is at B. So let's have a think about what's going on at B. Let's rub that out. So at B, my tension is going to be in this direction over here, and my weight is going to be acting in this direction over here. So when we're using Newton's second law radially, the F stands for the net force towards the centre of the circle. Well, the weight is acting perpendicular to the centre of the circle, so we're not going to include any of it at all, and we're just going to have our tension. So I'm going to say my tension is going to be equal to, and it's going to be mv squared over r, so this is going to be m, and the velocity at b squared over r. Okay, so again we know the mass and the radius, and our velocity our velocity at b squared, we worked that out earlier, and it's over here, and that's a value of 54.2. Okay, so that is already our velocity at b squared, 54.2. So if I come back over here, I know that my tension is going to be equal to 0.1 times 54.2 divided by 0.5, and again in my calculator I can work that out. 0.1 times 54.2 divided by 0.5, and that gives me a value of 10.84 newtons. Okay, so this should be my tension at A, I should have written, and this should be my tension at B. Okay, right, so my tension at C now. Well, let's have a think about what's going on here. I'll just rub that out for the time being. So I'll use a different colour again. So at C, I've got my net force towards the centre. I'm still got my tension that's going to be going that way, and this time I'm also going to have my weight that's also going to be acting that way as well. Okay, so both things are going in the same direction. So my net force this time is going to be the sum of these. Yeah, so my net force towards the centre of the circle is going to be the sum of these. So over here I'm going to say, well, that tells me that T plus mg this time is going to be equal to mv at C mv c squared over r. Now again, we worked out the velocity of at C squared earlier, and that's 44.4. So we can put in these values that we know. So that's going to be 0.98 is equal to 0.1 times 44.4 divided by 0.5, and again I'll use my calculator to work this out. So we've got 0.1 times 44 divided by 0.5, and we will subtract 0.98, and that gives us a value of 7.9. So that's telling me the tension at C is equal to 7.9 newtons. Okay, we'll just check to see whether that's right, and it's in fact 7.9 newton. Okay, the last part here is just to give us an idea about what's going on. It says, what is the tangent, sorry, I'll say that again, what is the tangential force at each point? So at point A, the force acting at a tangent at A is actually going to be 0. There's nothing acting at a tangent to A here. Similarly, at a tangent to C, there's no forces acting at all. Yeah, both forces are acting down here, and at A the tension is acting up and the weight is acting directly down. At B, however, the tension was acting towards the centre of the circle, and then we had our weight that was actually acting at a tangent to the circle. Okay, so that weight would have been at mg, which would be 0.98 newtons in this case. So at A we've got 0 newtons, at B we've got 0.98 newtons, and at C we've got 0 newtons. Okay, so we're now going to have a look at how we can work out the tension in the string at point D, which is at 35 degrees to the down direction here. Okay, so we need to know what the net force is radially, so towards the centre of the circle. So as we can see, our tension is going to be acting this way. So we've still got our tension acting this way. However, our weight is acting directly downwards, but some of our weight is going to be taken away from our tension towards the centre. Okay, so our net force this time is going to be made up of these two forces here, and in this direction we're going to have our weight 0.1 g, and it's actually going to be cos 35. So put that down, 0.1 g cos 35 degrees. So our net force here is going to be our tension take away 0.1 G cos 35 degrees. Okay, and it's take away because it's going away from the center of the circle, this component of our weight. Okay, and that's going to be equal to mv squared over r, so that's going to be 0.1 and the velocity of d, so velocity at d squared over r, which is 0.5. Now conveniently earlier we worked out what the velocity of d squared actually is, and we've got the value of that as 62.2. So I can now rewrite this as t take away 0.98 cos 35 is equal to, and I'm just going to change this to vd squared over 5, I've forgotten what it is now, 62.2 divided by 5, yeah, because 0.1 divided by 0.5 is just the same as a fifth, so that's just the same as dividing by 5. Okay, so I can now work out my tension. It's going to be my tension at D, and that's going to be equal to, calculator, so we've got 62.2 divided by 5 equals, and we're going to add on to that 0.98 cos 35. And that tells me that it's 13.2 newtons. Okay, we'll just check that over here, and it's in fact 13.25 newtons, which is, we rounded this number here. Okay, so if we would have used the exact version of this, then we would have got 13.25 newtons, but I'm happy with 13.2 newtons for the time being. Okay, so that's how you go about working out these problems. So the key thing, or the key part of this, is to realize that this here is always the net force, and that's always going to be towards the center of the circle, and we can work out the v squared part, or the v part of this, by using the fact that we know the total energy in the system, and that's always going to be consistently the same in any problem like this that you're solving, if it's a closed system. So that means if there's no external forces acting at all. Okay, finally, just to finish it off, I'm going to give you this problem to see if you can write what the tension in the string at E is in terms of theta. So if you pause the video, and I'll reveal the answer in a few seconds. Okay, hopefully you've got this here, or something equivalent to this over here. Okay, thanks very much for joining me, and I'll see you next time.